You're watching Force 13's live streaming service.
All right, and welcome here to Force 13 Astronomy Hour, at least the first one that I've been able to do here. And oh dear, what is this? Okay, so that's all the moons and stuff. All right, so I have a little bit of a presentation here for you guys. I wanted to do a 1-hour talk on exoplanets here because that is an area that is really fascinating to me and to the astrophysics community for sure. And I think that honestly, before you go out and look out for other systems, I want to talk a little bit about our own solar system because before we were able to look out and detect exoplanets and detect other systems, we've always taken a look at our own solar system and we've tried to figure out, okay, how did our solar system come into existence? And that is pretty simple, actually. We thought we had this down pretty well. And that is, well, we had all of the inner planets here. They're the small and rocky ones. You got Mercury, Venus, Earth, Mars. The small rocky planets. They're in the inner solar system. Meanwhile, we have these 4 gaseous planets out here: Jupiter, Saturn, Uranus, and Neptune. The reason why they look weird is because, well, they have this particular simulation actually has all of the moon systems here. So if I go in, zoom in, wow, here are all the moons. All of them, which is quite impressive to have on one simulation. Which is one of the things I love about Universe Sandbox, by the way. This is an excellent program, and I really recommend anyone viewing to put out the bucks to get this software because it is really something else. There's a lot of stuff you can do with this that I think is quite impressive. But anyways, as far as the origin of the solar system, we thought that all of the heavier, dense materials, they all condensed in towards the center because that's where they're hotter. Obviously, the metals can condense underneath very hot temperatures, and that's why we have inner rocky planets. Meanwhile, the ices and gases couldn't condense until you got further out here in the solar system, and that's why we have the 4 gas giants. Well, we thought that this was actually a pretty good description for everything that was going on until we started actually looking out for other planets. And then we realized something very weird just with the first planet that we found around a sun-like star, and that is going to be 51 Pegasi b. Now, this one is a weird one for the most part. And that's because, like I said, we have this idea that all of the rocky planets were going to be in towards the center, in towards the sun, because that's where all of the hot metals are going to be able to condense. You're not going to find rocky planets far away from the center or the ice giants close into a star. And then we find 51 Pegasi b, which seems to be one of these gas giant planets that are orbiting very, very, very close into the star. And I mean very close into the star. You take a look at the orbital radius for this thing, and it is, well, that's not the orbital radius. That is the orbital radius. If you take a look at the orbital radius, you can see it's only 0.05 of an astronomical unit. So we're talking well inside of Mercury's orbit. If I want to put in the habitable zone here, you would notice that the habitable zone, well, that's in the green, and the edges are in the blue and the red. And you can see that this planet here, 51 Pegasi b, is well inside all of this. And not only did we never expect to find a gas giant so close in to a star, we never expected to find anything so close into a star. And that's because we thought that, you know, they would form further away in a little bit of a cooler zone. Plus, if the planet's really close into the star, tidal interactions will end up slowly sucking in the planet if it ends up getting too close. It does not seem to be the case, though, for 51 Pegasi b, however, because it seems to be going at its own pace, minding its own business here, going around its planet, going around its parent star at a very, very close speed. We can see here the orbital period is only 4 days, so a year for this planet is only 4 days, which I think is just incredible to think that a planet could be so close into a star. And we thought, okay, well, this is an odd one. This is just an odd occurrence. You're going to expect to find the usual anomaly. Oh boy, were we wrong. We found a lot of these systems that had a lot of planets that were in very, very close to their stars. Another perfect example of that is the Kepler 10 system. Now, Kepler 10 is actually very, very similar to our own sun. It's only a little bit less massive than our sun, and it's a little bit more old than the sun. It's a little bit older than the sun. And we found this one planet that was in very, very, very close to the star. Again, well within the orbit of Mercury here. You take a look at it, it's even within the orbit of 51 Pegasi, as this is only 2/100ths of an astronomical unit away from the star. We're talking only 2.5 million kilometers away from its own star at any given time. And this creates some very interesting side effects. What you'll notice here is that, first off, with a planet this close to its star, of course it's going to be tidally locked to the star. And what that tidal locking means is that basically once two bodies get very, very close to each other, the smaller body will tend to have one side always facing the larger body and one side always facing away from it. And what you'll notice here, as I stop the simulation, is that there is a very noticeable hot spot here on Kepler 10b, where the magma on the surface is really superheated. We're talking temperatures of at least 3,000 degrees Celsius here on the hot side. And then as the storm orbits around, goes around its star, and you go to the cool side, what you'll notice here is that, of course, the crust is still melted because it's so close to its star. But you'll notice here that there's actual crust that you can be on. There's actual cool crust. And that's obviously a product of it having absolutely no atmosphere, and any Earth-sized planet like this one wouldn't have any sort of atmosphere this close to its star. I don't care what its magnetic field is. It would just never have an atmosphere this close to its star. It would just blow it away. And I think that's just quite incredible. Temperatures, again, like I said, we're talking 3,000 degrees on the sun-facing side here, and it only gets down to about 1,000 on the non-sun-facing side, which is still extremely hot, but just barely cool enough to where you can see patches of actual land where you can land on. And if you go further out, yeah, you can see that there's another planet out here. And this is a super Earth, Kepler 10c. And this is at least expected to be some sort of a water world where 91% of the world consists of water. And by the way, this planet is also probably too close to its sun to even be considered to be habitable. The average temperature on this planet is approximately 50 degrees Celsius, and that is way, way, way higher than what we have on Earth, which is around 20. So basically what's going to happen here with this one is that what would happen is very similar to Venus. It would have some sort of runaway greenhouse effect that would happen. And I don't have this shown here, but I will have this shown in another simulation that I will show. But again, I will zoom out, and what you'll notice here is that Kepler 10c, even that is on the inner ring of the red. This is still well within the habitable zone. The orbit is actually still within the orbit of Mercury here. So even though we're talking about, hey, we got this planet that is very, very, very close into its star, only a 100th of an astronomical unit away, 2.5 million kilometers away from its star, which again, that is unbelievably close to a parent star. Meanwhile, we have Kepler 10c here, which is sort of hanging out in what would be known as the sort of outer fringes. But at the same time, this is still closer than anything that we would really expect, because Mercury, this is still within the orbit of Mercury, and we weren't expecting to find any sort of planets within the orbit of Mercury around a sun-like star like Kepler 10. We would never think of that. And of course, we would find things that are absolutely weirder. These are actually the first exoplanets that we ever found. And these are weird, to say the least. So this is a system that actually has 3 planets around it, and they were named Drager, Poulter, and Phobetor. And Drager is actually the least massive known exoplanet in the entire solar system. It's only a little bit more massive than the moon. So this is the smallest known planet that we have. We have a couple of other ones here. We have Poulter, which is about 4.3 times the mass of the Earth. And we have Phobetor, which is 3.9 times the mass of the Earth. We don't really know too much about these planets, except for the really weird thing that is at the center of this system. These planets didn't form like you would normally expect a normal solar system, because the way that you would expect a normal solar system to form is that you would have this protoplanetary disk, that forms from a nebula, and you have the star condensing. Eventually it turns into a star, and then the leftovers would eventually get turned into the planets, and whatever materials would be used would end up being used. However, this one is super weird because these planets aren't orbiting anything ordinary. These planets are orbiting a pulsar, and that's what the PSR B21257 plus 12 stands for, is that these planets are actually orbiting a pulsar, and that's what this is. This is a neutron star, and that means that this is actually a supernova remnant. Which, again, that's just very surprising. You wouldn't expect to see planets orbiting a supernova remnant. Any planet orbiting a star massive enough to go supernova would have been blown away completely from the massive explosion that would happen from a supernova. So the question is, how did these planets get here? And it's systems like these, and systems like Kepler 10, and systems like 51 Pegasi that really questioned what the origin of these solar systems are. Where do these planets come from? Because our current methods of determining the origin of our own system doesn't explain what happens here. it does not explain how these planets could have formed from a supernova. It doesn't explain how there is a Neptune-sized planet within the orbit of Mercury going around a sun-like star. We have no explanation for any of that, or at least had no explanation for any of that. And that's when the idea of planetary migration came into effect. So I'm going to go back to 51 Pegasi really quick here. Play that. So, as I've already said, you aren't going to expect to see a Jupiter-sized planet orbiting very close to the star and have it being formed there. That's not going to happen. What is much more likely to happen, because there's not a lot of metals. When you take a look at these stars, they're only comprised of 2% metals. Most of everything else is hydrogen and helium, and of those 2% of metals, most of that is ices. So that would be methane, water ice, ammonia, all of those very basic chemicals that you would find. Everything else is extremely rare. So like silicon and carbon and all that stuff, those molecules, they do exist, obviously. If they didn't exist, we wouldn't be here. But those molecules do exist, but they're in very, very, very small amounts. And that's why you get very, very small rocky planets forming close into a star. And what you'll have here with the larger planets is that the ices can eventually condense. And they could get a lot bigger. Now, ices aren't going to be as dense as the rocky metal planets, but there will be a lot more of the ices by mass. So they can condense, they can create a much stronger gravitational pull, and from that gravitational pull, they'll be able to pull in the hydrogen, they'll be able to pull in the helium, and that is what ends up creating these ice giant planets. So now the question remains, how is there one of these giant-sized planets orbiting this close into a star? And that question has been pretty much answered by planetary migration. And basically what we expect here is that we don't expect that this planet formed here. No, we expect that this ice giant formed way out beyond, in this blue region, out beyond the blue region. So in a circle out beyond the blue region. And that something eventually made 51 Pegasi b spiral in and become very, very close to its parent star. Now, we aren't necessarily 100% sure what mechanisms might cause it, especially in a two-body system like this. You wouldn't expect anything to cause it. Obviously, there had to have been some third body to disturb this system in order to get a planet like this so close into its star. Because, again, the metal content, there is not enough of these metals by mass in order to create a gas giant planet. So there wouldn't be enough gravity. Even if all of those metals were to condense into one big planet, there wouldn't be enough gravity in order to maintain all of that hydrogen and helium, especially so close into a star. You're not going to find that. What you will find is that these ices will end up coalescing further out from the star, and you'll get these giants forming out here, just like in our solar system. However, it is likely that there's been a third body that interacted with this system and eventually migrated this planet inward. It could have shot it in on an elliptical orbit and eventually became circular. It could have been very much the case that it already had inner planets, and what happened was that 51 Pegasi b, because of its massive gravitational influence, being half the mass of Jupiter, was able to just absorb all of those planets and take in all of that mass as well, And that ended up changing its trajectory into an orbit where it is right now. It's very unknown what could have caused this, something like this to happen. But that is pretty much the gist of some of the weirdness that has happened. Now, that's planetary migration, but that's great and all, but that doesn't explain how we have 3 planets orbiting a supernova remnant, a pulsar. This is something that's really weird. First off, because pulsars had only just been discovered. So we didn't really know anything about pulsars at all. Pretty much at the time. Well, I don't want to say we didn't know anything, but we didn't know much about pulsars at the time. And they're still pretty weird, to say the least. But there's 2 things here that really point out that these planets didn't form. These aren't planets that formed from a protoplanetary disk. And the first thing is, and I don't know if you'll be able to notice this, but maybe if I zoom out here. Well, what you're looking at here, if I zoom in like this, if I angle it like this, you're looking top down on the system. But what you'll notice is that the orbits are actually inclined to the rotational axis of the pulsar by about 50 degrees, actually. And with the normal protoplanetary disk, you would expect all the planets to be in line with the solar equator. That has not happened here. These 3 planets are all pretty much aligned in with roughly a 50-degree inclination. So these aren't the same planets that was there before the supernova remnant. These planets had to have condensed from the supernova itself. Because where else are these planets going to come from? And these planets actually formed from the supernova explosion. And it's expected that these pulsar planets could in fact be carbon planets, where you can actually find multitudes of diamonds on them, which I think is something that is really, really cool with these systems, is that there is actually going to be a massive abundance of metals, because that's what you're going to get in a supernova explosion, because that's when you get a really massive star, and that starts forming everything. Carbon, nitrogen, oxygen, neon, argon, all gets everything pretty much all the way up to iron. And it's great. You know, if supernova wasn't able, if a star was not able to produce all of those elements, then the solar system and the universe as we know it would be totally different. But of course, that's only how you form the first 26 elements. How do you get the other elements? Well, they're formed in the supernova itself. The supernova is actually so powerful that it fuses together every other known element that we know above iron. So every other element above iron, that was formed in a supernova. And that seems very weird, because these supernova events are very, very rare. And you would be absolutely correct. So why is there seemingly so much of these very heavy materials? And that's because that's how big these supernovas are. It's a tremendous and unexplainable amount of energy that's released from these explosions. So it's expected that these planets, which would be in a cloud very, very rich in metals, that these planets could very well be very, very rich in carbon, and could potentially be these sort of weird diamond planets where they're made up of like just straight up carbon. It's really difficult to describe, honestly. But anyways, another thing that we ended up looking at when we went on the hunt for exoplanets is, and of course this is kind of an homage to the Star Wars fans, because we know, hey, there's this planet in Star Wars that has the 2 suns. Well, maybe there's a planetary system that goes around a binary star system, and yep, that's the case. That happens. We do have that. We have the Kepler 47 system. We have Kepler 47a, which is about 1 time, about the mass of the sun. And we have Kepler 47b, which is pretty much a red dwarf. It's about 3/10 of the mass of the sun. It's really not much. And this system actually has 2 planets going around it, surprisingly enough. We have Kepler 47ab-b, which I think is just a phenomenal designation. And this is a planet that's around 2.5 times the mass of Earth. And you take a look, and I know the simulation isn't exactly coming through very smooth, and that has to do with the screen share. But you can see here very clearly the 2 stars that it orbits. If I can even take off the trails really quick, and the labels, there you go. And that is just a pretty shot. That would be your normal day where you'd see your much larger sun-like star and then a much smaller companion star with Kepler 47b. And this is pretty much the planet's everyday life, is that it ends up going around these 2 stars. And actually, the orbit's stable. These 2 planets are both far enough away from their parent stars to where their orbits are, for the most part, completely stable. 47a and 47b, they're pretty much stable. And Kepler 47ab-b and Kepler 47ab-c, which is an even better designation, they're obviously not massive enough to disturb the Kepler 47ab system. So the only thing that the planets need to worry about is making sure they don't get too close to the stars. And right now, Kepler 47ab-b and c, they orbit the barycenter of Kepler 47ab, and not necessarily just one of the 2 stars. Now, if it was orbiting one of the 2 stars, that would likely be a problem. But this is an example of planets actually orbiting outside of the double star system. And here is Kepler 47ab-c. Now, this is much further out than B. Kepler 47ab-b is actually too close in to the double star system in order for it to be habitable. I don't know if you saw the temperatures, but the temperatures would be around 250 to 270 degrees Celsius. And obviously, that is way too hot for life as we know it. But we have Kepler 47ab-c, which is about 6 times the mass of the Earth. And this planet is too far out in order for it to be habitable. As you can see, the temperatures here are roughly minus 50 degrees Celsius. And obviously, that is way too cold for life as we know it. We can't have life as we know it at all on this planet. If I click on the habitable zone, what you'll notice is that there's actually going to be 2 habitable zones that pop up. And you'll think to yourself, oh, wait, here, Kepler 47ab-c, that is right on the inner edge of the habitable zone. Shouldn't that be clear to go? And you would think that for a second, but then you realize, well, look at how reflective the surface is. The surface is highly reflective. And that would be the cause of it not having a very high temperature. And here you have, oh wait, we have Kepler 47ab-b. Isn't that inside of the habitable zone? Ah, but that's the habitable zone if it was only orbiting Kepler 47b, not Kepler 47a, which is the main heat source. You have to realize that these 2 stars here, they basically they have a combined luminosity here. And that combined luminosity would basically be Kepler 47a. I mean, it's basically the entire output of the system. So this inner habitable zone basically means nothing. But you do see this double habitable zone pop up in Universe Sandbox. And when that happens, that just means that it's a double star system, and the star with the most power output, in this case 47a, would be the dominant factor in the climate of the system. And now I want to talk about at least my most favorite extrasolar planetary system. And this is going to be the Gliese 581 system. And this system is a very well-known one, mainly because of its multitude of planets going around it. And you can see here, there's plenty of them. We have Gliese 581e, B, C, G, D. And there used to be one thought to exist way out here, Gliese 581f, but that has been permanently debunked. And Gliese 581g, we aren't 100% sure of that planet's existence either. So that is one thing to get clear, is that Gliese 581g, we're not 100% sure of that planet's existence. And F, we used to think that exists, but that has been definitely been debunked. That doesn't exist. So let's start talking about some of the planets in this system. So we'll start furthest in. And first thing that should be known is that these planets are all very close into the star, but they have to be, because Gliese 581, the parent star, is actually just a red dwarf. It's only about 3/10 of the mass of the sun, and the luminosity is only about 1/50th of what the sun is able to put out. So not even that. So the Gliese 581 is much, much, much weaker than them. So even though these bodies are all orbiting in very, very close to their star, you'll see this one here is orbiting 2/10 of a quarter of an AU out from Gliese 581. So that's still well within the orbit of Mercury. However, this star is a lot smaller, so the planets are going to be a lot closer in, because the frost lines are going to be different with the cooler star. And I'll pull up the habitable zones here, and what you'll notice is that there are 2 potentially habitable planets. Probably the best one is the still yet to be confirmed Gliese 581g. If not, probably Gliese 581d is the better candidate. However, D does have a noticeably eccentric orbit, as you can see here, and that does take it pretty far out. It has an eccentricity of around 0.25, which is roughly about the same as Pluto. So a fairly eccentric orbit. You can definitely tell that there is an oval shape to this orbit, rather than the typical circles that we would be accustomed to in our solar system. But anyways, without further ado, let's get in and start talking about the planets to this system, because I think that every single planet in this system is just interesting in its own right. And this is Gliese 581e. So the first one here, and this is basically this system's Mercury. It's the closest into the star. It's the smallest planet in the entire system, at about 2 times the mass of the Earth. Yeah, smallest planet, 2 times the mass of the Earth, I know. But still, Gliese 581e, the smallest planet, and it is not going to be the hottest planet in this solar system. That will likely be Gliese 581c, for reasons that I'll get to when I get there. 581e, obviously too close into its planet to hold, too close into its star, rather, to hold an atmosphere. The red dwarfs tend to be very active. They have a lot of solar flares, very strong solar wind. So a planet like Gliese 581e that doesn't have a lot of mass to it, even though it's 2 times the mass of the Earth, even though it doesn't have a lot of mass to it, the atmosphere blown away on this. No atmosphere, and we're talking about a temperature of around 220 degrees Celsius anyways, so no water, no chance of life, but basically this is this system's Mercury. And then we talk about Gliese 581b, and this is one of those hot Neptunes again. This is a gas giant that formed well out in this system that eventually migrated inward, somehow managed to not take out the planets on exterior to this, C, G, and D, somehow didn't touch those, and it migrated into this system. Because again, gas giants aren't going to form close into a star like this. So this had to have migrated in here. And this planet is around 16 times the mass of the Earth, or in Jupiter terms, about 0.05 times the mass of Jupiter. So basically nothing compared to Jupiter. This planet's cloud top's temperature, this likely has very reflective cloud tops, so the temperature only about 102 degrees Celsius. And that is really surprising to find when you realize that this planet is only 4/100ths of an astronomical unit away from its star. I mean, the star is right there. It's only 4/100ths of an astronomical unit away from the star, and the cloud tops here are barely at boiling point. So that is Gliese 581b. Due to a highly reflective surface and the star not being that strong, again, only very small fraction of the luminosity, only very small fraction of the power output compared to our sun, that this planet very, very well inside the orbit of Mercury. In fact, this would be inside of the orbit of 51 Pegasi b, and this planet here only has a cloud top's temperature of maybe the boiling point of water, maybe even less so. And I think that's just fascinating. And now we get to what is likely the hottest planet on this in this solar system, and that is Gliese 581c. And the unfortunate part here is that despite my best efforts, I have not been able to have this software render this planet's atmosphere. I don't know why. It's just refusing to render the atmosphere, but that is just how it is, unfortunately. So what it would be, again, very reflective cloud tops, pretty much like Venus. It would have an atmospheric pressure of 106 times atmospheric pressure here on Earth, very similar to Venus. And that would create a surface temperature of around 470 degrees Celsius, very similar to Venus. Basically what I'm saying, this is this exoplanet's Venus. And that is really the case because it's 5.3 times the mass of the Earth, which is, yeah, that's very, very massive, no doubt about that. But this planet, you'll notice here that this planet is well inside of the red. And the reason why we suspect that Gliese 581c has this very, very thick atmosphere to it is because of the same reasons that Venus had the very thick atmosphere, is that it would end up losing its magnetic field and slowly lose its water over time. And what that would end up having is that you would end up having a runaway greenhouse effect. And this planet would have more than enough mass to trap that kind of a thick atmosphere. So that runaway greenhouse effect has more than likely occurred here on Gliese 581c. So that is why we expect that Gliese 581c is this planet that is very, very similar to Venus. So we've already talked about the planet that's very similar to Venus. We talked about a planet very similar to Mercury, and we also have a hot Neptune in here because of course we do. It's exoplanets. But now to talk about the unconfirmed, now I'll keep on saying this, the unconfirmed, but very much Earth-like planet that is Gliese 581g. Now, this planet, if it ever were to be confirmed, is the closest Earth-like planet to us, just period. And I think that's absolutely astounding. This entire planetary system is only 22 light years away, is Gliese 581. So this is only 22 light years away, and this would be one of the closest Earth-like planets if this were to ever be confirmed. 4 times the mass of the Earth, and as you can see, The temperature here, 12.4 degrees Celsius. And that's very similar to the Earth, with an Earth-like atmosphere and an Earth-like greenhouse effect and all that stuff. Surface temperature, 12.4 degrees Celsius. And it does need that atmosphere. And two reasons why it needs that atmosphere. The first one is because it is still very, very close into its star. We're at about 1/10.5 of an astronomical unit here. So about 3 times the distance than 51 Pegasi b. And that is still further in than half the normal distance between the Sun and Mercury. So this is still very close into the star. So that tidal lock that I was talking about for Kepler 10, that is likely still going to occur for Gliese 581. One side is likely going to always face the star, one side's always going to face away. However, if it has an Earth-like atmosphere, it would be able to distribute the heat all across the planet, you know, just like our planet, obviously. We don't lose all of our heat when the sun's not up. So a very similar effect will happen here, is that the atmosphere will try to evenly distribute the heat that is absorbed by the planet. And that will likely create some very turbulent conditions, probably strong winds, obviously, on a planet like this. But it is very possible that a planet like this could pretty much, if this ends up being confirmed, I'm pretty much convinced that there would be life on this planet, I think without a doubt. Even if you take a look at this program here, this says that it has an Earth similarity of almost 91%, a life likelihood 1 in 4. And that's huge, honestly. A life likelihood of 1 in 4, better than 1 in 4, I think that is a very good probability considering the vast harshness that is out there in the universe, and the fact that there's a planet, allegedly a planet like this, only 22 light years away. If this were to ever be confirmed, this would be huge news. Huge news. But again, it's still, unfortunately, an unconfirmed planet, but I have my fingers crossed every single day that this thing ends up getting confirmed. And just to know that that's probably the best bet right there if we ever needed to get off this planet. Now, actually doing interstellar travel, that's a completely different topic, and that's a completely different political debate that I really don't want to get into in this. Is interstellar travel feasible? Will we ever be able to get to that? It's debatable. Anyways, there is one more planet to discuss, and that is Gliese 581d. And this is about 7 times the mass of the Earth. So this is pretty much halfway in between one of those ice giant planets and one of those terrestrial planets. It's like on the borderline. Is it like Neptune? Is it like Earth? This one's really hard to tell. We wouldn't be able to really know. You notice that it has a 62.9 degrees Celsius temperature. That mainly has to do with a thick atmosphere. Its effective temperature is actually minus 100 degrees Celsius. So if it had no atmosphere, it would be a very, very, very cold place. And that's actually pretty much the same for Gliese 581g as well. If it didn't have an atmosphere, it'd be a very cold place to live. And Gliese 581d pretty much is like Gliese 581g in many ways, if it ends up being an Earth-like planet. But as I said, the noticeable thing about Gliese 581d is that it has this very noticeable eccentricity. So if you take a look at the surface temperature, the effective temperature really, it varies wildly throughout the year. So you see it comes in close to the star and it ends up getting all the way up to minus 60 degrees Celsius. And then it ends up going away from the star. And again, because the star is very, very small, since the star is very, very small, a slight nudge in an orbit for a planet here will affect the temperature even more dramatically than it would in our solar system. And you can see it's almost gone down by a factor of 2 with an effective temperature all the way down to minus 106. So again, it's unknown if anyone would even be able to live on this world because it's one of those borderline cases. Is it a gas giant? Is it a terrestrial planet? We really don't know, and we really wouldn't ever be able to know unless we were able to, even if we were able to get a good spectrum of these planets, we still wouldn't be able to tell 100%. Is it a gas planet? Is it a terrestrial planet? We're still trying to figure stuff out. I know a classmate of mine, his name's Corey. He was... No, not Corey. Never mind. I'm thinking of something else. I was thinking of someone else. I'm sorry. But anyways, another classmate of mine, a different classmate of mine, he was using one of those computer algorithms, one of those artificial intelligence algorithms, to try to determine, okay, which planets go where and by what characteristics would he be able to tell if it's a terrestrial planet, if it's a confirmed planet, or if it's likely a false positive. It was kind of inconclusive, to say the least. It was some cool stuff, no doubt about it, to look at it, but it was some inconclusive stuff. So we have a long way to go from being able to tell borderline cases like this if they were a gas giant planet or a terrestrial planet. It's kind of hard to tell. So that is pretty much a tour of what is my favorite extrasolar system. And well, I think the best way to go is just to go back home where we know. Let me find it here. There we go. And just think, you know, this is what we're used to. This is what we know. And that is our 4 inner planets, our 4 big outer planets. And you can just see that there isn't necessarily the same order to these systems than what we expected. We expected, of course, every single system to end up like our own. And in hindsight, that was probably a little naive of us, but at the same time, we never really had any reason to question what we knew. And these planetary systems that are out there, they really do make us question what do we really know about our own solar system? And the real answer is that we really don't know too much. And it's crazy to think like that, but it is really the case, is that we really don't know that much. There's a lot of stuff that we do know. We've got Newtonian gravity down to a T. We're able to calculate, you know, relatively long periods of orbits. We're able to figure out, okay, where certain planets are going to be, where everything's aligned. We can make perfect predictions for that. We know all of that. But there's still a lot to learn about the origin of our solar system. There's still a lot to learn about, you know, where the sun came from, really how the sun formed. We got the basic process down, but there's still some questions that need to be asked. And it's a really interesting exploration that we've been undergoing these past few hundred years to try to figure out where we've come from. And I think this look out to find these other weird, extreme planets, finding these planets that are orbiting neutron stars that already have exploded in massive supernovas that should have no planet, should never have a planet orbiting it. And the first And the first system that we ever find, it's a pulsar with 3 planets orbiting. We were never expecting that. That caught us way off guard. 3 years later, we end up finding a star with a Jupiter-sized planet orbiting within the orbit of Mercury, around a sun-like star. This was shell shock. It was a real shock to the scientific community. We weren't expecting stuff like this. We were expecting system, for the reasons I explained early on in this presentation, we were expecting to find solar systems very similar to our own, where we have these rocky planets in close to the star, and the Jupiter-sized planets way out beyond. And I think that was just it was short-sighted of us to do that, and I really think that we should learn from this experience and realize that even if we think that we've known everything, even if you think that you've figured out everything that you possibly can, there's still other ways to gather information, and there's still other ways that you got to look at things. No matter how sure you are, and I really think that this goes for everything too. This doesn't just go for space exploration. This doesn't just go for astrophysics. This applies for everything. That even if you think that you know everything about a certain topic, there's still more out there for you to learn about. And even if you think you got everything nailed down, you got everything perfectly explained, you got to always question yourself, do these models generalize? And this is actually a very important thing for artificial intelligence in the future. If we're going to start using these machine learning algorithms, there is a very important thing called overfitting the data, where you'll have a model that explains one scenario very, very well. Just like we had with our solar system, we had the one model that explained everything very, very well. And then as soon as you looked elsewhere, that model was instantly pretty much broken to shreds. And we needed to go back to the drawing board and be like, okay, how do we explain this? How do we explain this? How do you explain this? And you always have to be thinking in the back of your head, okay, well, what if this happens? What if this occurs? And it's always nice to think in the hypothetical sometimes, even though you can't get too crazy, you can't go completely out of bounds with the hypothetical, but there are some cases where it'll just blow your mind how crazy the universe is and how crazy just life is in general. You always need to approach everything with an open mind, and that is very key to basically to the scientific thinking, is that you always have to keep an open mind, keep an eye out for new opinions and new ideas, and always be ready to have your ideas challenged, and be ready to change your ideas and your models and your perceptions. And this is just a perfect example of this kind of thinking and the scientific community coming together and overcoming the overfitted model that we have of our solar system to say, okay, how did these Jupiter-sized planets end up close into the sun? Well, they had to have migrated inward. There's really no way that they could have formed there. We know that. So
Devon, can I come in?
Yes.
I just have a few questions.
Yeah, sure.
You look at our solar system and the amount of planets we have, and I've always been led to believe, at least, that we are a statistical anomaly in that we have a larger amount than what we've seen in other solar systems. How much of an anomaly is that?
And that's one of the things, is that we really don't know how much of an anomaly it is. I think the most that we've found in an extra solar system, I think the most that we found is 6. But you also have to realize how difficult these planets are to detect, And you also have to realize that the orbital periods start getting very large for the planets that are further out from the star, but aren't exactly far enough away from their own planet, their own host star, to be individually imaged. So, and we haven't been detecting these exoplanets for very long, and we haven't been focusing in on one system for very long either. We've only been detecting these since 1992. So you got to consider that a lot of these planets that will have orbital periods of, say, 5, 10, 15 years, usually you need several of these orbits in order to confirm an exoplanet's existence. And that's why we're finding all of these hot Jupiters and all these planets that are very close into their stars, because those planets with the short orbital periods are the easiest ones to detect.
Can I ask a question about the normal Jupiter?
Yes.
I think I glanced at a story that happened recently about one of the probes getting to see the poles of Jupiter. Can you shed any light on what they've been finding, if anything, up there?
Yeah, I have not been paying attention to the latest Jupiter mission, to be honest. So I'm not 100% sure what they're finding, but I do know that there is an active spacecraft currently investigating Jupiter. I can't remember what the name of it is.
It's on the tip of my tongue.
I can't remember what the name it is, but I do know that there is a spacecraft actively investigating Jupiter. I think it is. I wanted to say Juno, but I know that there's also this probe that they sent out towards, I think it was Vesta, in the asteroid belt, and they wanted to investigate. It was either Vesta or Ceres, one of those two, and they wanted to investigate that. And I thought that was the one that was Juno. Maybe it's the same craft. I'm not 100% sure. It could be very easily that it could have hit Vesta and Jupiter. But
I guess just the final one for me as we finish out this fantastic hour that we've been watching. It's certainly been enthralling to me. I've been sitting here listening. Do you want to make a mention of what, outside of, I mean, I don't know if you count Earth's moon, but which moon out there in the solar system fascinates you the most?
All right, well, that is a very easy question for me to answer. And that is looking into the Saturnian system. And Saturn is a very, very interesting planet. And I'm planning to, with Astronomy Hour, I'm planning to eventually make a full-fledged presentation with Saturn. And the Saturnian system is very interesting. Of course, you have the ring system, which isn't showing up here, but that's because I'm not on the actual Saturn simulation. And it also has a ton of very interesting moons, Prometheus, Mimas, and Enceladus, to say the least. But the most interesting of all of the Saturn moons, and I'm trying to find it, there it is the moon Titan. Now, this is the second largest moon in the entire solar system, next to Ganymede. And this is the only moon in the solar system to actually have an atmosphere. And I'll show you that right now, that it does have an atmosphere, as I should be able to come into the program and turn it off if it will let me. There we go. And there we go. You can turn it off, and you can notice that this planet, well, this moon anyways, it pretty much is a planet. And it has this really weird surface where it's very, very cold, but ice is actually its rocks. And it has hydrocarbons on the surface, and there's 100 times more oil on the surface of this planet than we'll ever find on Earth. And there's just so much rich carbon on this planet that it's entirely possible that it could have ended up forming its own form of life on here. And it's entirely possible that there's forms of life that we haven't even thought of, and they exist right here in our own solar system. Well, thank you very much for showcasing this fantastic episode of Astronomy Hour, Devon. It's time for us to finish up here at Force 13 HQ. Okay.
And we've not decided what time you'll be back for the next show, but we're guessing it's going to be something like a month's time, and something like that.
All right. That's fine by me. I really enjoy doing stuff like this.
We've enjoyed watching it. I certainly have. Well, that's all from us right now. Thank you very much for that, Devon. And I guess just a reminder of the latest information that we've got from the storm situation right now. Typhoon Trami still a Category 2 at this time. And I don't think there's any new information on that as we take over. I wonder if the JTWC have any graphics out there, but I haven't seen anything recently. And Tropical Storm Kirk moving through the Lesser Antilles pretty soon, not just yet, but a tropical storm warning out on a lot of those islands, Barbados and a large swathe of the Lesser Antilles, and Hurricane Rosa headed towards the Baja California Peninsula. Slowly but surely, it will be a few days before it gets anywhere near. And the tropical storm in the southern Pacific Ocean, Cyclone, I forget the name of it already, it happens quite often, Liua, Category 1 on the Australian scale. Fiji think it will get to Category 2 on that scale. And that pretty much covers everything. That is a very rare storm. Only one of about 5 September cyclones to do so. That's all from us for now. We'll be back again at some point in the near future. No later than Friday, because Friday, of course, is games night. And we're probably going to be doing Guess the Storm again. I don't know. We'll see. Obviously, you can find out the latest on the YouTube channel. And on our social media pages, Facebook and Twitter. Search Force 13 all in text. That's all from us tonight. It's been a great night here. We'll see you again soon.